Imagine you are standing in a room. In front of you there is a wall. Your goal is simple. Walk towards it. You take your first step, a big one, that covers half the distance between you and the wall. That was easy enough. Now, you stand at the halfway point. For your next step you do the same thing. You cover half of the remaining distance. You are now 3/4 of the way to the wall. You are getting closer, which is exactly what you wanted. The wall feels much nearer now, its texture and color more defined. You can almost feel the cool plaster against your fingertips. You decide to continue this pattern. From your new spot you take another step, covering half of the tiny distance that is left. Then you do it again, and again. Each step you take is smaller than the last, a mere fraction of the previous one. The gap between you and the wall is becoming incredibly small, almost imperceptibly so. You can see every tiny crack and imperfection in the paint. So, let's put a more formal but still friendly name to this idea. In mathematics, a limit is the value that a function or a sequence approaches as the input gets closer and closer to some specific value. Think back to our wall analogy. The function was your rule for walking. Always move half the remaining distance. The input was the number of steps you took. As the number of steps you took got larger and larger, your position got closer and closer to the wall. The wall is the limit as your steps approach infinity. It's a way to talk about infinity in a controlled way. Mathematicians needed a tool for spots without a clear-cut answer. What happens right at the edge? What is the value at the moment of impact? Sometimes you can't just plug in a number and get a neat answer. Limits. Let us peek at those tricky spots by looking at the behavior of numbers all around them. It's like judging someone by consistent patterns over time. Limits don't care if the function reaches the destination. In our wall example, you never touch it. There might be a hole, a gap, or a completely undefined point right where we want to look. Limits sidestep that problem by focusing on the journey. Let's make this even more concrete with a simple numerical sequence. Consider the numbers. 1/2, 3/4, 7/8, 15/16, 31/32, and so on. At first glance it might just look like a list of fractions, but there is a clear pattern here, one that mirrors our walk towards the wall. Each number is getting a little bit bigger than the one before it. 1/2 is 0.5, 3/4 is 0.75, 7/8 is 0.875, 15/16 is 0.9375. The numbers are growing, climbing upwards, but their growth seems to be slowing down. Where are they heading? Each number is getting closer and closer to the number 1. The difference between each term and 1 is getting smaller and smaller. Do you want to be within 1/1,000,000th of 1? No problem, just go far enough along in the sequence and you'll find a fraction that does the job. This is the core idea of a limit in action. This idea of getting infinitely close to something is not new. It has puzzled thinkers for thousands of years. The ancient Greek philosopher Zeno of Elea came up with a series of paradoxes that illustrate this problem. His most famous one involves a race between Achilles and a slow-moving tortoise. To make the race fair, the tortoise is given a head start. Here is how Zeno's argument goes. Every time Achilles reaches where the tortoise was, the tortoise has already moved on. This process continues forever. It describes an infinite series of smaller and smaller tasks. How can someone complete an infinite number of tasks? It seems impossible. And that was Zeno's point. He had stumbled upon a fundamental problem that mathematics would need centuries to solve. That tool is calculus, and it is built upon the concept of limits. A limit tells us that even though there are an infinite number of steps, the total time and distance they represent adds up to a finite value. The limit of the sum of all those tiny time intervals is the exact moment Achilles overtakes the tortoise. Zeno's paradox is a perfect, ancient example of a limit waiting to be discovered. Let's leave ancient Greece and return to a more familiar setting, the kitchen. Imagine you have a glass with a maximum capacity of 250 milliliters. You also have a magic tap that dispenses water in a peculiar way. The first time you turn it on, it gives you exactly half the glass's capacity. That's 125 milliliters. The next time, it gives you half of the remaining capacity, 62.5 milliliters, for a total of 187.5 milliliters. You can probably guess what happens next. You turn on the tap a third time and it adds half of that, which is 31.25 milliliters. Your glass is getting fuller and fuller, getting closer to that 250 milliliter mark. Each burst of water is smaller than the one before, a diminishing splash that fills a shrinking void. Will the glass ever be perfectly full? Following the rule of our magic tap, the answer is no. It would have 249.999. and so on, with the 9s stretching on forever. This is another perfect real-world illustration of a limit. The function is the rule of the magic tap. The input is the number of times you turn the tap on. The limit is the value that the total amount of water in the glass is approaching, 250 milliliters. We can say with absolute mathematical certainty that the amount of water is tending towards 250 milliliters. The limit gives us the destination value. Let's think about a situation where precision is key, like in a professional bakery. Imagine a baker who wants to create the perfect cake. The recipe calls for a very specific oven temperature, say exactly 175 degrees Celsius. If the temperature is too low, the cake will be underbaked, too high, and the outside will burn. A real oven doesn't sit perfectly at 175 degrees. The element turns on, the temperature rises, then the thermostat turns it off. It might go to 176, then fall to 174 or 173 as the thermostat cycles. The cycle repeats. The oven's actual temperature is constantly fluctuating around the target. The baker's success depends on the oven's ability to limit this fluctuation. A good modern oven will have very small fluctuations. It might only vary by half a degree in either direction. As the oven settles down, what temperature is it approaching? A good oven's temperature has a limit of 175 degrees. Its average behavior centers precisely on that value. Engineers define a tolerance. As long as fluctuations are small enough, we treat the oven's temperature as 175 degrees for practical purposes. This is how engineers and scientists think. Get close enough to the ideal for the real world to work. So far we've talked about approaching walls, filling glasses, and baking cakes. These give intuitive feel for what a limit is, but the real power of limits is unleashed in calculus. Calculus is the mathematics of change, and it could not exist without limits. Limits are the fundamental building block, the foundation of calculus. There are two great big ideas in calculus, and both are defined using limits. The first big idea is the derivative, the instantaneous rate of change. Think of the speed of a car at a single precise moment. It is calculated as a limit. It measures change over an incredibly short period of time and finds the limit as that period approaches zero. The derivative is the limit of the average speed as the time interval shrinks to nothing. The second big idea is the integral, used to find total amounts as they accumulate. Mathematicians slice the area into an infinite number of thin rectangles and take the limit as widths approach zero to get exact area. Without limits, we would be stuck with clunky approximations. Limits give a rigorous way to handle zero and infinity, letting us zoom in on an instant or add up infinite pieces to get exact answers. They are the microscope and the telescope of mathematics, exploring the infinitely small and the infinitely large with precision. The importance of limits isn't confined to the abstract world of pure mathematics. Because calculus is the language we use to describe the physical world, limits are at work all around us. They are embedded in the technology we rely on and the science that explains our universe. Once you know what to look for, you can see their influence everywhere, the mundane and the magnificent. Think again about the speedometer in a car. It calculates instantaneous speed, a derivative, which is a limit, but the applications go much further. When engineers design a bridge, they model stresses with calculus and compute load limits as load increases. Consider a satellite. Equations of motion determine the exact velocity needed to reach a stable orbit. Its velocity is a tangent vector to the orbital curve, found by a derivative. Get that limit wrong and the satellite burns up or drifts into space. In economics, marginal cost is the rate of change, a derivative. That tells firms whether increasing production is profitable. From wing design to population models to computer graphics, limits drive the calculations behind design and prediction. Even medical imaging reconstructs 3D from 2D slices using calculus-based reconstructions. Limits are implicit. In all of these, the concept of the limit works silently in the background. So, after our journey through walls, paradoxes, kitchens, and calculus, what is the simple truth we can take away? The mathematical concept of a limit is based on an intuitive idea, getting closer and closer to a destination. It's not about the arrival, but about the journey and the undeniable trend. A limit lets us talk about tricky spots, points at infinity or infinitesimally short moments, by observing behavior nearby. The limit is that magnetic point, the value the function is irresistibly pulled towards. Derivative and integral, both built on limits, let us model and predict the changing world. A limit is simply a destination. It's the value you are getting infinitely, undeniably, predictably close to. Understanding the direction of your journey is often the most important thing of all.